Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to implement a parameterized policy in Theano for the continuous version of Mountain Car. If you don't want to code along, although I strongly recommend you do so, the relevant file for this lecture is pg theano.random.py in the subfolder Mountain Car. At the top, we have all our usual imports. Next, we have the hidden layer class, although I am not going to make use of it in this lecture. We are just going to use a linear model with RBF kernels. You are encouraged to try to turn that off and use a plain neural network if you want. Next, we have the policy model class. This is going to be similar to before, but with some extra functions around copying. At the top, we declare some hyperparameters. And then we copy all the arguments from the constructor. This is so we can make clones later. Next, we create the layers for the mean. Remember that the mean is unbounded, so the final layer activation function is identity. Next, we create the layers for the variance. Remember that the variance must be greater than 0, so the final layer activation is soft plus. Next, we collect all the params. Remember that we need to collect the params from both the layers for the mean and the layers for the variance. Next, we create shared variables for the cache and velocities to be used in the updates later. Technically, we don't need to do any fitting since we're doing hill climbing, but theoretically you could do both in some combination, so I leave that option up to you. Next, we make params an instance variable. This will be useful later when we do the copying. The next step is to declare inputs, advantages, and actions as before. The getOutput function is useful since getting the output for both the mean model and the variance model is the same. We add a little bit of smoothing to the variance to aid in exploration. Next, we create a function for the log PDF of the Gaussian. This is a formula everyone should be familiar with by now. Next, we specify the update rule. This is the same as before. You can choose between different types of optimizers by commenting things out. Finally, we compile the train op and the predict op. Notice how the predict op now returns both the mean and the variance. Next, we define the predict function. This will return both means and variances, of course. Next, we have the sample action function. This part is different from what we've seen before. First, we need to call predict to get the mean and variance of the Gaussian. Keep in mind that x has only one sample. The first thing returned by predict is a list of means, and the second thing is a list of variances. So we index by 0, 0 to get the first mean, we index by 1, 0 to get the first variance. Next, we generate a sample from the standard normal, scale it by the standard deviation, and add the mean. Now, because the environment only allows actions between -1 and 1, we need to clip this sample to make sure it's in this range. Next, we have some functions related to the hill climbing procedure. First, we have the copy function. This creates a new policy model with the same constructor arguments as it had originally. Then it calls the copy from function, which copies the parameters from one model to another. Next, we have the copy from function. Since we saved the parameters as an instance variable earlier, now all we need to do is loop through them. We can use the useful functions getValue and setValue to get the numerical values of each parameter. Next, we have the perturbParams function. This is what will help us do the hill climbing. So what we do is, we loop through each param, and then with probability 0.1, we just assign a new random setting to the param. Otherwise, we take the current param and add some noise to it. Next, we have the play1 function. This one's pretty simple. Next, we have the play multiple episodes function. This just plays a bunch of episodes and returns the average reward. Remember that we want to play multiple episodes to test each parameter setting to reduce the variance. We also want to test how well our model can do over 100 iterations, since that is how you're judged on OpenAI Gym. We also have the print iters argument that will print the average after each episode, so that you don't have to wait for all 100 episodes to see the result. Next, we have the random search function. This is very similar to the random search we saw earlier. First, we initialize total rewards to be an empty list, where we'll be collecting the rewards for each parameter setting. Then we initialize best average total reward, which helps us keep track of the best parameters we've seen so far. Next, we have best P model, which will be the actual model containing the best parameters. Then we have the number of episodes to test each parameter. I found 3 to be sufficient. Next, we do a loop 100 times. I found this to be sufficient for finding a good setting of parameters. In the loop, we make a copy of the best model, we call it temp model. Then we perturb its params. Then we play a few episodes with these settings and obtain the average reward. We append this to our list of total rewards. If this average total reward is better than the best we've seen so far, then we set the best model to be this new model. Then we exit, returning both the total rewards list and the best model we found. Next, we have the main function. This is mostly what you expect. We create the environment, feature transformer, and the model. We have our code block for monitoring. Then we do a random search. We print the max total reward. Then of course we want to check these parameters for consistency, so we play 100 episodes and print the result of that. Finally, we plot the total rewards as a function of time. Notice how we are not plotting the cost to go function. This is because this method doesn't require a value function at all. Although technically, now that you have a policy, you can use policy evaluation to calculate it. I leave this as an exercise for you if you're interested. Let's run this and see what we get.